Hello, my amazing students. This is Mrs. A. We are starting 9.2 and I did 9.1 in class, and then I finished up with a 14-minute clip to finish that one up, which is posting right now. So we're doing 9.2 and then 9.3, and then that will be the last of your lesson videos, and I will start on your homework videos so that all of the material will be out there for you to study. So I'm trying to get everything done so that you have a full week of them being online in order to get all the material before the final exam, which is 1 week from today. So here we go. All right, so we are starting 9.2 here, and notice 9.2 is all about testing the difference between means. We're going to start with small independent samples. That's what we're going to do most of, and then we'll have a very brief discussion about large independent samples towards the end of 9.2. So independent means that two samples are independent if the sample values from one population are not related to or somehow naturally paired or matched with sample values from the other population. And two samples are dependent or consist of match pairs if the sample values are somehow matched, where the matching is based on some inherent relationship. Okay, so we're going to deal with dependent samples in 9.3. 9.2 is dealing only with independent samples. So here is a picture of independent, dependent. Independent have no relationship. There's only 4 in that sample, and there's 7 in that sample. They're not matched at all. This is a paired sample. Dependent samples are paired and somehow go together. All right, so we're going to classify the pair of samples as independent or dependent. Weights of 65 college students before their freshman year begins, and weights of the same 65 college students after their freshman year. Well, these are going to be dependent. They are paired. It's the same students. It's just before the freshman year and after the freshman year. So this is dependent samples. The samples can be paired with respect to each student. Okay, scores of 38 adult males on a psychological screening test for attention deficit hyperactivity disorder. Scores of 50 adult females. So it's the same test, but the samples are completely independent. So they're independent, not matched. There's no possibility of pairing between the members of the samples. The sample sizes are different, and the data represents scores for different individuals. Okay, so hypothesis test. These are the objectives for this section. We're going to conduct a hypothesis test of a claim about 2 independent population means. Our minor objective is just confidence intervals. The confidence interval, I just want you to know how to do it. We will not be stressing that, but you may see some homework problems that ask you for a confidence interval, and it's very simple, as I showed you today in class, to just plunk the go over to the confidence interval, because the data carries from one test to the other. You don't even have to re-enter it. That's pretty simple. Okay, so when we're talking about our null hypothesis is always going to be the one that has the equal sign in it. This is the same as from chapter 8. When we talked about that, we went into null and alternative quite detailed in chapter 8. So hopefully you got that material already. And when we're talking about this is the same thing that we wound up doing in chapter 8, these same situations, except here we're talking about mean 1 and mean 2 of the 2 different samples. So remember that the 2 hypotheses always cover all of the situations possible. And regardless of which way you set these up, you will always assume that there is no difference between the population means. That's going to be your assumption when you start out. So here are your notation items here. Mu1, population mean of the first sample. Mu2, population mean of the second sample. X bar 1, sample mean. X bar 2, sample mean of the second situation, and so forth. So that's your notation. And we're going to talk about what conditions must be met in order for us to do this test, okay? Notice what kind of test we're going to be doing. Sample t-test. When we're doing the population proportion like we did in 9.1, we always use the z-test. But now we're in means and we're going to use the t-test. Notice what we're starting out with. If samples of size less than 30 are taken from normally distributed populations, a t-test may be used to test the difference between the population means mu1 and mu2. 3 conditions are necessary to use a t-test. Okay, so small independent samples. The samples must be independent. The samples must be randomly selected. Each population must have a normal distribution. Remember how we judge normality. Normality is either they tell you it's basically normal or you have an n greater than 30. So you have to have that met before you can even use the t-test. The biggest reason that we're going to be using the t-test, though, is because we do not know the standard deviation. It's assumed we do not know the standard deviation to start with this. So just like in Chapter 8, when we were testing the mean, we did not know the standard deviation. We used the t-test. All right, so here are the requirements. The values of sigma 1 and sigma 2 are unknown, and we do not assume that they are equal. So that's kind of the start of what we're doing here. The 2 samples are independent, both samples are simple random, and we have normality either or both of these conditions are satisfied. The 2 sample sizes are both large, or we have populations that are both normally distributed. We will use the t-distribution for critical values because we have an unknown standard deviation. So here is the test statistic for the t-test. And again, this is what you would do if you were doing it by hand, but we're going to get to do it with the calculator, which is going to make it much nicer. We do need to know how to get our degrees of freedom, though, because when we're doing the t-test, we're going to have to determine when we use what, and if we were going to do it with the comparing with the critical values on the t-score, we would need to know what we're using for our degree of freedom. And this is the confidence interval, which we're really not going to worry about the confidence interval much because we're going to use our calculator to do this for us if we need it. We just use a 2 sample t-int, and that will give us the confidence interval whenever we are asked for one. Again, this is a secondary goal of this section, not really that important. I just want you to know where to find it when you are asked. Okay, so listed below are student course evaluation scores for courses taught by female professors and male professors. Use a 5% significance level to test the claim that the 2 samples are from populations with the same mean. Does there appear to be a difference in evaluation scores of courses taught by female professors and male professors? Okay, so now, what is the claim? To test the claim that the 2 samples are from populations with the same mean. So the claim is same mean. So since the same mean would be equal mean, then the alternative hypothesis will be unequal. All right, so we check our requirements. Do we have the normality that we need? Do we have independent samples and simple random samples? Now, we didn't do quantile plots, but this is just an example. You're not going to have to use quantile plots on the test. I will either tell you that it is basically normal, or I will give you an n greater than 30, or you will tell me I can't do this test. All right, so here we're starting to set up our problem, and we're assuming the claim is that the two means are the same. This is our alternative hypothesis, and so we state our H sub O and we state our H sub A, and now we proceed using this assumption. Now, if U1 minus U2 is equal to U2, then U1 minus U2 is 0. The 0.05 is our significance level. And then we're testing a claim about two population means. We use the t-distribution. And there's our by hand t-statistic. But we're going to do this on the calculator. And here they've got the stats that were given. Now remember, they did not give us these statistics. They gave us these values. Where is it? There we go. They gave us this. So basically, in order to get the X bar, they had to average those all up together. Okay? Or we can do it using stats and do an L1 list. Okay, which is what we'll do here, just so that you can see how to do an L1 and an L2. So here are the, here's the test statistic that we got. And so when we're doing a p-value, we're going to use the number of degrees of freedom, n-1 and n-2, whichever is the smaller of those two. So we had 12 minus 1 and 15 minus 1 because we had two different size samples. So when we get that, we get 11, the smaller of the two. So degree of freedom is 11, and it's a two-tailed test because of the not equal to the H sub A. So we're going to p-value greater than 0.20. Now they're going to the table, and they're using the t-distribution to get that. But we're going to use our technology, and we're going to get a more accurate p-value. And then in step 7, because the p-value is greater than the level of significance, we fail to reject. Okay, so it says if p is low, the null must go. The p-value is greater, so we do not reject. So here we go. There's not sufficient evidence to warrant rejection. But we're going to, now they're doing this with their Excel stat, which we don't have access to, but it still gives you all of those critical values, gives you the critical value, the observed value, and then the p-value. We don't have access to that, but we're going to use what we do have access to, which is our two-sample t-test. So we're going to do this from stats instead of data, and we're going to use the values that they gave us when they figured them out. And then we're going to come down here, and notice I said it's not pooled. We only pool when we have dependent data or when we're doing the proportion test. So we're not going to pool them. We're going to end up getting the p-value is here. So 0.51718, and the t-value is negative 0.6599. All right, so let's go look and see how that was comparing to what they gave us. Okay, so here was the observed t-value, negative 0.6599, and we got negative 0.6599. When they calculated it using the formula, they got negative 0.66, but 6599, you can see how that will round. So we're usually going to get more accurate if we use the technology than if we go ahead and do it that way. Now they went ahead and did their they had their technology spitting out their critical value. We don't have that option. So we're going to have to find our critical value from our t-chart. So let's go over to look at our specifications here. And we have a level of significance of 0.05 split into two tails. So let's go find the t that's going to go with 0.05 split into two tails. All right, so here is our t-chart. We're looking at 0.05 area and two tails. So we're going to say area and two tails 0.05. We're going to run down this one. Remember, our degree of freedom was 11, so we're going to run across and we're going to get 2.201 from the chart. But technology gave them 2.09 and we're getting 2.201. So there is a difference, but basically it's not going to affect our rejecting or failing to reject, because whether it's 2.09 or whether it's 2.20, we are nowhere close to being in the tails. Okay, so whether you use 2.09 or whether you use 2.20, the tails are way over here, and our test statistic was negative 0.660. And we are well within the normal region, not out into the tails, so we will fail to reject whether we use a t-value or test statistic, whether we use a critical value or whether we use a p-value. All right, let's go back to this screen at the beginning of this problem and notice that we are given data instead of calculated values. They're giving us the raw data here. So I went back and did it with the raw data, and here is my screen. Hopefully you can see that, where I did L1 and I listed all of the top row, and I did L2 and listed all of the second row. Okay, so I listed them all the way down here, so that keeps on going until I finish with the 15 and the 13, and they don't match. The two samples are not the same. One's females and one is males. But when I go back here, that's where I got those stats. So now, notice that after they did the requirement check, they calculated for us those stats. Okay, well, suppose you had to do that on your own. So here I've got my L1 and L2. So they're already entered in. So I'm going to come over here and I'm going to go to stat, and then I'm going to move over to calculate, and I'm going to go to one variable stat. And when I go to one variable stat and I put in my enter, I'm going to hit enter here, somewhere down there. And then it says, where do you want me to take the stats from? So I'm going to hit enter again because I want the first stats to come from L1. And when I do, I get 3.86666 repeating. And then down here for the standard deviation, I get 0.5630006, which matches this first set of data right here. Okay, and that was for the females. That was the 12, which I had listed first. And then when I go over here to my stat and edit again, and then I look at my L2, and I'm going to do stat and calc, and I'm going to go to my one variable stats, but this time when it's blinking, I'm going to put in L2, which is just a second button and the 2 button down here, and it goes L2. You see the L2 up there? So now I'm going to hit enter, and I get the L2 stats, which matches my second one down here. So 3.99333 and 3.993333. Okay, and then this one is a standard deviation of 0.3954, and this one is a standard deviation of 0.39545, which is exactly the same thing as that. So that's what you can do if you're ever given data and you're not given these values right here. But once we get those values, we can go straight to our t-test. So since we're doing the t and we're on means now, we're no longer on standard deviation, we're going to go to our stat test. Let me see if I can lower this down. Test, and we're going to go down to, get my down key here, and sorry about that. We're going to go down to a 2-sample t-test. When we go down to a 2-sample t-test and we hit enter, then it's going to ask us for our x bar 1 and our standard deviation 1, x bar, our number in our first sample. So we enter all of these things, which I'm going to do very quickly for you, entering the things that are here on the screen. Then I enter this data. I end up getting this on my screen, which is very, very close to the values that they got before. Okay, so this time I used the stats that were already provided here. Now I'm going to use the data that I have entered in. So I'm going to go back to my data here, and I'm going to hit enter. And now it's going to say, do you want me to go to L1 and L2? Well, that's where I have the data stored. And I'm still going to keep this not equal to, no pooling. And I hit enter. And when I do, I get something very, very close to what I had before. In fact, if you go over here to their values, they had the t observed negative 0.6599, and we've got negative 0.6599. And then there, we don't have a t value on ours, but we do have the p value, and they have a 0.5172 because it's two-tailed. They've already doubled it, and we, for our p value, have it also doubled here. So basically two-tailed, no, we have to double that. I think they're telling us that we have to double it. So, yeah, maybe it's already done for us. I'll have to look at that and see what you calculate if you actually go there. If you go to the t-score, they may have already doubled it because they do so much of it for us in here. I bet you they've already doubled it for us, but we do have the same thing that they have there. That would be a good thing to check. So 0.51 though and 0.05, the p-value is definitely greater than the alpha. Okay, so these were the slides that I had made for you so that you could see when I did it with the calculator, so you could follow through with those. So now the critical value method, we can do it with the p-value or the critical value. When they're doing it with the p-value, they're looking at the p-value 0.5172, okay, and if the p-value is low, the null must go. If the p-value is going to be less than in the tail, then the null must go. So it depends on when you're looking at the tail, the p-value's got to be in it. So that pretty much covers that one. So here's the critical value method. When we did the critical value with the t-chart, we got 2.201. When we did it with the technology, we got 2.093. It really did not matter because our test statistic was negative 0.660, and it was definitely not in the tails. Therefore, we failed to reject. And, all right, so here we go with the next slide is alternate methods. Assume that the two sigmas are equal to each other and pool the sample variances. The pooled estimate of sigma squared is denoted by SP squared and is a weighted average of S1 squared and S2 squared. The cool thing is, guess what? We don't have to do this math. The degrees of freedom is to note here N1 plus N2 minus 2. If we had to do it by hand, we would have to do that by hand as well. If we are looking for the critical value to go with this, we would need to use this degree of freedom in our chart. Other than that, you don't have to do the math, because here goes. This is the confidence level that goes with it. Again, you can use your confidence interval, your SAMP T int will give this to you because it will tell you, it'll ask you whether you want to pool it or not. And you just say, yes, pool it. And you don't have to do the math. Here's your test statistic. Again, you don't have to do that math. And there's your confidence interval. So basically, this is when your sigma 1 and sigma 2 are known. We're going to do that a little bit later on in the PowerPoint. When the sigmas are known, you can use a z-test. And so you will just do it on your calculator. You will do the confidence interval on your calculator. Not a biggie. Now, this is your author. And your author's recommended strategy for two independent means is to always use the t-test. He says, unless you are told otherwise, you're going to use the t-test. Now, if they tell you the two sigmas are the same, then yes, you should pool them. If they tell you that you know your sigmas, then yes, you should use your z-score. But they're saying anytime you're approaching a problem, you're going to assume that you do not know your sigmas. You're going to assume that the two sigmas are not equal to each other, and you're going to use the t-test. Okay, so unless you are given sufficient evidence that your two sigmas are the same, don't pool. Pool only when they tell you that your two sigmas are the same. Okay, so it says pool only when your sample standard deviations are the same or very close to the same. So unless that is true, you're going to always go with the first method, which is just to use the t-test and do not pool. So here is a little cool flow chart that tells us when to use the normal distribution and when to use the t-distribution for means. Okay, it says, are both samples at least 30? If both samples are at least 30, then yes, you can assume normality and use the z-test. If no, then it says, are both populations normally distributed? If you say no, you can't use either test. If you say yes, then it asks you, are the population standard deviations known? If the population standard deviations are known, we're going to use the z-test. If the population standard deviations are not known, we're going to say, can we use the t-test? Are the population variances equal? Okay, so if they are, then we're going to pool them. Okay, we're going to use the t-test with a pooling. If the population variances are not equal, we're going to use the t-test with non-pooled. So basically, these are both using the t-test, and we don't have to do that math. All we have to do is tell it whether to pool it or not to pool it. So ours is a little bit easier because we're using technology. So here, let's go and make some decisions here. So this is kind of the little cheat sheet chart. The degree of freedom changes, and when we're looking up our degree of freedom, we need to know whether we're looking up a pooled sample or non-pooled sample, because we're trying to find our critical value that goes with our problem. We're going to use our t-distribution to find those critical values. We do not have to calculate our test statistic. We're going to use our t-distribution to do it for us. We're going to use our two sample t-test, and it's going to do everything for us. So let's practice here a little bit. It says the results of a state mathematics test for random samples of students taught by two different teachers at the same school are shown below. Can you conclude that there is a difference in the mean mathematics test scores for the students of the two teachers? Notice the question is difference or not a difference, so we're going to have equal and not equal. And it says, assume that the populations are normally distributed and the population variances are not equal. So we will not pool. And so we're going to go through here, and they calculated the test statistic by hand. We're going to use the same information with our technology, but here their calculated t statistic is not in the rejection region. Okay, so the rejection region is determined by the 90%, the 0.10 that's going to be in two tails. So 0.05 over here, and the t-score that goes with that is, they're saying, is 1.895. Because we're looking at a t-score, our degree of freedom is important. So we would look under degree of freedom 7 and 0.05 in one tail. And that's going to give us, okay, so here's the 7 going across to 1.895. And notice that's the 0.10 in two tails, or the 0.05 in one tail. So that's where they're getting their 1.895. They're taking their calculated t-score here, their test statistic, and they're comparing it. 1.895, and our t-score is 0.922, well within, not out in the tails. So we will fail to reject H sub O. Our H sub O was that they were equal. We will basically not be able to reject that. Therefore, we will support the claim that the mathematics test scores for the two teachers are different. I said that wrong. There is not enough evidence to support the claim that the mean test scores are different, because we could not reject the fact that they were the same. So now on this next slide, I have the steps for the test here. And we did not pool them, and these were just some, it's a 2-sample t-test that we're going to do. We are not going to pool them because the two variances are not equal, and you can just try that and see what you get. All right, I went ahead and entered all of that for you and got the t-value of 0.9224, which is the same thing we had right here. And the p-value, which we did not calculate here, was 0.379, so we could have done a p-value test here. And then when we scroll down here, we end up just showing our values there. So we still got the 0.922, and notice that we did not get the same degree of freedom. We used a degree of freedom of 7 here, but that doesn't matter because this is giving, we're doing an estimate. When we use our degree of freedom formula, this is giving you the degree of freedom as calculated by the technology, which is more accurate, but we don't really need the degree of freedom because we did it with the technology sample. All right, so here we have another example, and a manufacturer claims that the mean calling range in feet of its 2.4 gigahertz cordless telephone is greater than that of its leading competitor. You perform a study using 14 randomly selected phones from the manufacturer and 16 randomly selected similar phones from its competitor. The results are shown below. At alpha is 0.05, can you support the manufacturer's claim? Assume the populations are normally distributed and the population variances are equal. So since the population variances are equal, we're going to use the pooled button on here. So now what is the claim? The claim is that the mean calling range is greater than, that's going to be our alternate hypothesis there, because, and then the less than or equal to will be our H sub O. So less than or equal to will be our H sub O. Greater than is going to be our claim. Our alpha was the 0.05. Since it's pooled, we're going to add them together and subtract 2 to get 28. And Then we have, when we go to 28 degrees of freedom, we should get our test statistic there. And then we calculate our test statistic here, and we end up getting our t-score 1.811. That's a lot of work. I'm glad we get to use technology. And there's their 1.811. 1.811 is past the critical value of 1.701. Therefore, we're going to reject the H sub O. And again, let's look at how did they get the 1.701 if they are, because this is what's going to come back from your technology, is this score. How did they get this? They're going to look at 28 degrees of freedom and 0.05 in one tail. Okay, so here you have it. We're looking at 28 degrees of freedom right there. And we're going all the way across to the area in one tail being 0.05. So we're going to the second to the last column and 28 all the way across. And look at that. We've got 1.01, and that's right there. 1.701. 1.701 goes across to the 28 degrees of freedom right there. It's hard to see. Remember, when you get back your technology, you're going to only have a test statistic, but you'll also have the p-value, which you can compare to the alpha and do a p-value test as well. All right, so we had to reject H sub O because it was in the rejection region. Since we rejected H sub O, we're going to say that yes, indeed, the claim is true. We can support the manufacturer's claim. And here was the calculation screen. We're going to use the pooled variance because the two variances are equal, but we're still going to do the same two-sample t-test. Everything's the same, but we're going to hit the pooled button, and we could do that one just the same. So I'm not going to do that one on the calculator because I think I've done enough of those. So now we're going to say what happens when we have large independent samples or our standard deviation is known. When that is true, we get to use a z-test. Okay, so when we are told that we either have large independent samples or our standard deviation is known, we can use a t-test as long as we have all of the other qualifications taken care of. So here it says 3 conditions are necessary to perform a z-test. So we're going to look at those again. Number 1, the samples must be randomly selected, which is our normal. Samples must be independent. Each sample must be at least 30, or if not, each population must have a normal distribution with a known standard deviation. So the known standard deviation is really key because that's going to automatically tell you that you can use the z-test. If these requirements are met, the sampling distribution for the difference between the sample means is a normal distribution. And there's the standard error, there's the sampling distribution, and all of that cool stuff. But guess what? Again, you don't have to do all the math. You get to use your technology for z-normal. So we're going to use a two-sample z-test. Okay, so two-sample z-test for the difference between means. And we have a credit card watchdog group claims that there is a difference in the mean credit card debts of households in New York and Texas. The result of a random survey of 250 households from each state are shown. The two samples are independent. Okay, so we are definitely not going to pool these. Okay, they don't give it, they're definitely from two different areas. They should not have anything in common. So basically it says, do the results support the group's claim? So we're going to do a 2-sample z-test, but we will not pool. When we stick in all of the data, we've got the fail to reject because our z-score is definitely not abnormal, right? It's pretty small. It is definitely within this non-remarkable range here, and our negative 1.96 is our 0.05 confidence level for the z-score, which we can get from our critical value chart, and that one is pretty much done. We could do that again on our technology. Let's do that real quickly for a 2-sample z-test. So here we're going to go, move this over here, we're going to go to stat and test, stat and test, and enter, and we're going to go to, I keep on making boo-boos, we're going to go to 2-sample z-test, which is number 3 on mine, and we're going to hit enter, and we're going to do this from the stats, and we're going to use the stats as they are stated here. Okay, so we're going to have our X bar and our sample, and since we're doing a z-test, we can use our S1 in place of our sigma. Okay, so here we're going to plug those in. Great, so I plugged those all in, and instead of my sigmas, I used my S1 and my S2 because I have a large sample here. Because I have a large sample, I can assume I have a pretty good sample standard deviation that's going to be a good model for my true sigma. So on large samples, we can use the sample standard deviation in place of our sigma. And when I did that, remember this one was, they ended up getting the negative 1.11, and our z-score is negative 1.11 on our 2-sample z-test. And we end up getting all of this other stuff that we didn't really need to put in there. Our decision is going to be fail to reject because it's not in the rejection zone for 5% alpha there. Okay, so that's just doing a z-test. And you see that now we could use the p-value also. Okay, so the p-value here is right under the z-score, is 0.265, and this one is going to be compared with the 0.05, and it is once, and we have 27% or 0.265 to the right of the p-value, and over here we've got 0.05, which is going to make it definitely not in the rejection region. So we're going to fail to reject. Our p-value is much greater than our alpha. So we fail to reject our H sub O. And that is consistent. So now let's look at the next one. A travel agency claims that the average daily cost of meals and lodging for vacationing in Texas is less than the same average cost for vacationing in Virginia. The table shows the results of a random survey of vacationers in each state. The 2 samples are independent. At alpha is 0.01. Is there enough evidence to support the claim? So we're going to be using we have large enough samples here to use our z-test because we have greater than 30 on both of them. So we're going to use a 2-sample z-test with no pooling. So here I've entered all of my data, and now I'm going to come down here and scroll down, and I have a less than situation because it says Texas is less than the same average cost for vacationing in Virginia. That's the claim. So I'm going to use a less than, and then I'm going to calculate. Okay, so when I calculate, I get a negative 1.25. Now I'm going to do this one without looking at the next slide because I want you to go through the reasoning process here. So negative 1.25 is our z-score, and 0.1051 is our p-value. Okay, so we've got our z-score, negative 1.25. Is that significant? So we have to find what is our critical value when we're talking about an alpha of 0.01. Since we're using a z-test, we can go to 0.01 in our left tail. Okay, so let's do that. All right, so down here at 0.0099, I'm on my z-score chart on the left. 0.0099 is the closest I can come to 0.01. And I end up with negative 2.33. So negative 2.33 should be our critical value that goes with this problem. So again, looking at our test statistic, negative 1.25, and our critical value is negative 2.33, which is farther to the left than this is. So our z-score, that went away. Our value is to the right, not in the tail. So now that I got this back again, I'm going to go show you something different. So we're going to go down, and again, instead of calculate, we're going to draw. Okay, so I'm going to enter, and it gives me my values. And if I come down here and do an enter there, I don't know why I have to do that, I get the values that are there. So negative 1.25 is my critical z, and my p-value is 1.1051. Now it does not show me where my negative 2.33 is, but it's farther over here to the left. So it just helps you out a little bit to see where your z-score is. It's definitely not 2 standard deviations away, is it? So it's definitely looking like it's not abnormal, but then when you compare it to the negative 2.33, you can definitely see that. So now let's look at the rest of the screens here. So here were our claims, and they showed you the TI 8384 entering all the data in like I did, okay? And then we had the less than test because of our alternate hypothesis. We're going to use less than instead of not equal to. And then when we do it, we end up getting that for our z and that for our p-value. And if we draw it, we end up getting those on the screen, which is cool. It still does not make our decision for us because you notice that there's no place in here to put in the 0.01 alpha level of significance. But you get to make that decision. You just have all of this information that you get from your calculator. All right, so I don't know why my screen says click to edit master title style. That's not supposed to even show up on a slideshow. Oh, well. Okay, so here you can see my negative 2.33, which was my critical value. You can see my 0.01, which was my alpha. Okay, the 0.01 is the probability that something lies over there past that negative 2.33. My value, my z-score, is negative 1.25. Negative 1.25 is not in the tail, therefore I fail to reject, and there's not enough evidence to support the travel agency's claim. Now we are done with 9.2. So we will close this little video and do 9.3. And we really don't have that many more slides. I think we got about 30 more slides, and we will be done with all of our new material for this course. That will be very cool. And I'm kind of ready, aren't you? And this is Mrs. A, and may God bless your day.